chemistry students, welcome to your first lesson on solutions. In particular, we're looking at just a basic introduction to solutions, as well as looking at solubility and factors affecting solubility. So there are four main goals for this lesson. First of all, be able to identify the solute and solvent that are making up any given solution. Second one is to be able to define the terms saturated, unsaturated, dilute, and concentrated, and distinguish among those different things. Third goal is to be able to use a solubility chart to figure out how much solute we can dissolve into a given amount of solvent. And lastly, we will identify different factors that influence the solubility of a particular solute. So let's get started. So first of all, we just review some basics on different types of combinations of substances to understand what a solution is. So the first thing to consider is what is a mixture. Hopefully you remember. It's a combination of two or more different substances that can be physically separated. This is in contrast to a compound where those materials are actually chemically bonded together. So in this situation, we haven't created any new substance, just mixed multiple pre-existing substances together. Second thing to consider, what term do we have for mixtures where we can see all the different components that make them up? That term is heterogeneous, hetero meaning different, so we can see the different components in there. And lastly then, what is the term when we have a mixture where everything is blended together and it all looks the same all the way through? That term is homogeneous, homo meaning same, so it looks the same all the way through. So now if we place solutions within that context, a solution is a particular type of homogeneous mixture. So again, it's a mixture in which our different substances are not chemically bonded, they're just physically combined, and it looks the same all the way throughout. And in a solution, we have a situation where particles of one substance are dissolved and scrambled, interspersed among particles of a different substance. Some examples. Oh, silly Java. No, I don't. All right. Some examples of solutions that we might encounter are salt water, air, Kool-Aid, and a variety of other things. Ooh, the colors. Ooh. Right. Now, solutions are made up of two main parts. Now, the first part that we'll talk about is called the solvent. And the solvent is the term that we have for the majority of the solution. Whatever our biggest substance is that makes up most of our solution is typically the solvent. It is the thing that is dissolving our other component. A lot of the solutions that we will look at in chemistry will be, a lot of the solvents that we see for these solutions will be water, liquid water. Okay. The other main part is the solute. That's usually the lesser substance, and that's what's being dissolved into the solvent. Okay. Now when we combine those two together, we get a solution. So for example, if we were trying to make salt water, our solvent would be water. We would need mostly water. And the solute that we were trying to dissolve in would be the salt. We need much less salt. But we pour it in, those salt particles get dispersed among the water particles, and then the overall salt-water mixture is what we call the solution then. So some different examples then for you to consider. One solution that I find especially tasty is lemonade. Okay, and lemonade, again, the majority of it is water, so that is our solvent. The solutes that we dissolve into the water are lemon juice and sugar if we're going old-fashioned and making the real stuff. Soda is another example of a solution that we talked about last time we met. The solvent was water as well in that situation, and sugar and carbon dioxide would be the solutes, the lesser materials that are getting dissolved into the solvent in order to make a new solution. Okay. The air that we breathe is also a solution. In order to figure out what the solvent is and what the solutes are, we need to know the composition of air. As it turns out, it's about 78% nitrogen. So since that's the majority, that indicates to us that nitrogen would be the solvent in air, and all the other substances, hydrogen, oxygen, carbon dioxide, etc., would be solutes that are being dissolved into the nitrogen. And another solution that I enjoy wearing, 18 karat gold. 18 karat means that the gold is 64% gold, and the rest of it is miscellaneous other stuff. So since this is majority gold, we say that gold is the solvent, and the solute is all the other metals that get mixed in, typically a predominantly nickel alloy. Okay. Now moving on to our second goal, I'll start us off with a little joke. Why was the sleep-deprived chemistry student staring at the orange juice carton? Anyone? Because it said concentrate. Okay, anyway, so moving on with some new terms to define and describe our solutions. One is concentrated. Okay, so a concentrated solution is one that has lots and lots of solute in it. So a concentrated saltwater solution would be super salty. There's lots and lots of that solute salt in there. The reason you'll often see juice containers say made from concentrate, it means that really what they had was a concentrated solution with a high percentage of fruit and sugar, etc., which later got mixed with water in order to get you to a reasonable tasting juice. So concentrated means lots and lots of solute per amount of solvent. Okay. The opposite of concentrated is dilute, which I'm sure you've heard of, like diluting a beverage, for example, adding water to it. It means that we have a higher percentage of solvent, therefore. So dilute solutions then have relatively small amount of solute in them. If we had a dilute saltwater solution, it would not taste very salty. We wouldn't have much of that solute in it. Okay. Now, a couple other terms to introduce are saturated and unsaturated. Now, these are similar in some ways to concentrated and dilute, but they're a little bit different because now we're really looking at the maximum capacity of solute in our solution and how our solution compares to that. So for all solutes in all solution, there is an absolute maximum amount of solute that we can dissolve into it. If we have less than that amount of solute in our solution, we call that solution unsaturated, okay? It's got less than the maximum amount of solute. We could add and dissolve more solute if we wanted to. Okay, so for example, we see if we were to add 30 grams of salt to 100 milliliters of water, it would be unsaturated because we'd be able to dissolve all that salt and more if we wanted to. So that means it's unsaturated. A saturated solution then has reached its absolute upper limit in terms of how much solute it can take on. Okay, so to see that in action, say instead that we tried to dissolve 40 grams of salt into the same amount of water, 100 milliliters, what we would find is that the saturation point is 36 grams of salt in this case. So 36 would be the absolute maximum that this amount of water can hold, and the remaining amount can't get dissolved. That tells us that this is a saturated solution because we absolutely cannot dissolve any more salt in it. It has reached maximum capacity. Now, most people would look at a solution like that and say, okay, it's had its fill, we're going to leave it alone. But we, being people who are always pushing the limits, have found ways to actually, come on, there we go, supersaturate a solution, or in other words, push it even beyond the saturation point. Now, the way that we can do that is by heating our solution. As it turns out, for a number of solutes, and we'll talk about this a little bit more later, we can increase the amount of solubility of that solute as we raise the temperature. Okay, this is why when you make Jell-O, you're always told to dissolve the Jell-O powder in boiling water, even though you're going to refrigerate it later. It seems like extra work that doesn't seem necessary. But as it turns out, by adding the Jell-O powder to boiling water, we can actually cram more sugar and more gelatin into the water than that same amount of cold water would be willing to take. So we kind of trick the water into sucking up and dissolving more of that solute than it normally would. And then we trick it by then cooling it down once it's already dissolved all of that solute. So by doing so, we have created a supersaturated solution. We have tricked the water into dissolving more solute than it normally would. Okay. So again, the maximum amount of solute allowed, that saturation point, is going to be different for different solutes and different solvents. Okay. Now, for example, in 100 grams of water at 55 degrees Celsius, we can dissolve a maximum of 85 grams of potassium nitrate. However, if we tried to add salt, just an ordinary table salt to it, that water could only hold 36 grams before it reached its saturation point. So as we see, depending on the characteristics of each of these different solutes, we have different thresholds for how much can be dissolved into our solution. Now, in order to keep track of all these different solutes and how their solubility changes with temperature, we have solubility curves drawn on a solubility chart. Now, this is going to have a bunch of lines, but don't worry about it. We're going to walk through this. Okay. Now, if we see this graph right here, what we are seeing is the amount of solute being graphed on the y-axis. Okay, in particular, it's the grams of solute that we can cram into 100 grams of water. Okay, and on the x-axis we have temperature in degrees Celsius, varying from 0 to 100, since that's the range in which water is liquid. And each of these lines represents a different possible solute. So, for example, this line right here describes the solubility of potassium nitrate, KNO3, ranging from 0 degrees all the way up to, well, in this case, up to just 76 degrees or so, because its solubility just gets completely off the charts. Okay, whereas this curve would describe the solubility of ammonium chloride, for example. Okay, so we see that the solubility is going to be different for each of these different solutes at different temperatures. Okay. Now, first question to consider, does the solubility of sodium nitrate increase or decrease as we increase the temperature? So in order to figure this out, we go looking on here for the curve that describes sodium nitrate. If you need to refer to your ions chart, that's okay. But in particular, sodium nitrate is this guy right here, NaNO3. Okay? And what we notice is that at 0 degrees, we can only fit 73 grams or so of sodium nitrate into our water. But as we increase up to, say, 60 degrees Celsius, we can actually dissolve about 125 grams of sodium nitrate into the same amount of water. So if we see here, the solubility of our sodium nitrate is increasing as we increase the temperature. We can cram more and more sodium nitrate into our water as we heat up our solution. Okay. A couple more questions to consider. Okay. Say we have dissolved some compound in water and we've hit the saturation point of 61 grams of solute in 100 grams of water. Say we take the temperature and it's 70 degrees Celsius. We want to figure out which compound that this is that maxes out at 61 grams at 70 degrees Celsius. So in order to do this, I'm going to go to the temperature of 70 degrees and up to the solubility of about 61. Okay, and just see which solubility curve intersects it right there. In this case, it looks like it's ammonium chloride. That's the one that seems to intersect this point of 70 degrees and 61 grams. Okay. Now, a similar question. Say we've got another compound that has a solubility of 41 grams of solute per 100 grams of water at 50 degrees Celsius. Which compound is that? So same deal. I will look at the intersection between a temperature of 50 degrees and a solubility of about 41 degrees. So I will find that point right there and see which solubility curve it is that intersects that point. And what we see is that it's potassium chloride. That is the solute that intersects that point. Okay. Now, there are some ways that we can actually push this solubility point a little bit, that we can actually get a little bit more solute into our solvent than we otherwise would. In particular, there are 4 ways that we'll talk about here. Okay. First one seems like a no-brainer. First way to increase solubility is to increase the surface area of the solute. And that just really means spreading it out so that there is more exposure of that solute to the solvent. So for example, if I just put in a big like sugar cube into my water, it's going to be really hard for the water molecules to penetrate that big cube of sugar. Whereas if I crumble it up, I mix it up, I get it all interspersed with the water, it's going to be much easier for those water molecules to make their way in between the sugar molecules and get all of it dissolved. So that's our first way. The second way that we can increase solubility and increase the rate at which things dissolve is to heat our solution. Now this works only for solid and liquid solutes like the Jell-O powder that you saw in class the other day. Now by heating the solution, we're getting our solvent molecules to move faster, and that's going to cause them to collide more frequently with the solute molecules and get everything interspersed that much faster. Now a third thing that we can do, the opposite of the one that we just talked about, is to cool the solution. And this only works for gas solutes. So just to recap, we increase solubility of solid and liquid solutes by raising the temperature, but we increase the solubility of gas solutes by lowering the temperature. And the reason for this is that if we have a lower temperature, we're not going to have our gas molecules evaporating and escaping out of solution as quickly. That means more of those gas solute molecules are trapped inside our solution. This is what we saw with our soda. When we heated up the soda, more of those carbon dioxide molecules evaporated and escaped out of the soda, leaving us with a flat beverage, whereas a cooler soda can hang on to those carbon dioxide molecules for longer. Okay. Last way that we'll talk about is to increase the pressure being exerted on the solution. Now again, this only works for gas solutes. Now the way that this works is as we increase the pressure on the solution, it's harder for our gas molecules to evaporate out of the solution. Kind of like what we talked about in terms of how pressure changes the boiling point of water or any other substance. Okay, so if we increase the pressure, we're basically pushing all those gas molecules back into the solution and holding them there so that we can keep more gas in our solution. Okay. Now, I would highly recommend just kind of summarizing all of this with a chart. What we see is 4 different things that we can do: increasing or decreasing pressure, or increasing or decreasing temperature, and look at how that affects solubility of solids and liquids, as well as the solubility of gas solutes. Okay. Now if you want to test yourself, feel free to pause here and see if you can fill this out. If you have no clue, that's okay. Let's go through it right now. So if we increase the pressure, it has no effect on solid or liquid solutes because they're not really going to evaporate out. But by increasing the pressure, we increase the solubility of gases because we're pushing them down in there, keeping them from escaping out of our solution. On the flip side of that, then, if we decrease the pressure, we also decrease the solubility of gas because that means that it's going to be easier for the gas molecules to evaporate and escape out of our solution. Now, if we increase the temperature of our solution, what you should recall is that that's going to increase the solubility of our solid and liquid solutes because our molecules are moving faster and interspersing more quickly, but decreases the solubility of our gases because as we increase our temperature, we increase the rate at which our gas solutes are evaporating out of solution. And then on the flip side of that, if we decrease the temperature, we decrease the solubility of our solid and liquid solutes, but increase the solubility of our gases. Okay. Now just to check to see if you really got this, a few questions for you to consider. First, looking at the solution of soda, okay, we want to figure out what role carbon dioxide plays in it and what role water plays in it. Second question, how would the fizziness of a soda change if we move that soda to a place of lower pressure, like at a high altitude, for example? Okay. Third question to consider, how would we describe a solution when we only have a little bit of solute dissolved in it? Okay. So take a moment, consider these questions. Feel free to pause, seriously check yourself on this. When you're ready, come back. Alright, so here are the answers. First of all, in soda, Carbon dioxide is the solute, it is the lesser amount of material that is getting dissolved into the soda. Water is the solvent. It makes up the majority of the solution and is the thing that is dissolving the carbon dioxide. As for the solution, that's the soda, the overall mixture, the whole thing put together. Okay. For number 2, if we lowered the pressure, we would decrease the fizziness of the soda, because lower pressure means it's easier for those carbon dioxide molecules to escape, which leaves us with a flatter soda. And third question, the way that we can describe a solution in which only a small amount of solute is dissolved, the word we would use is dilute. Now, it's true that that's probably also an unsaturated solution, but in particular, dilute is the word that we would be going for here, because we're talking about a small amount of solute in particular, not just short of the maximum, but really, really small amount of solute. Okay, that's it for this first lesson. Please bring your questions to me next time we have class. Have a wonderful weekend.